So next problem is on page 334, and this is another example which I want to show you. This is connected with the, I think it's connected with the Stokes theorem itself. Let me just show you which one that is. So this is page 330, and we have problem number 8. So problem number 8 is this particular problem here. Can you see it? So this is the problem that I have. And well, I can tell you this is not an easy problem to do with, but I'm going to show you systematically how we can work on that. I'm going to call this part is called A, so I can calculate divergence. My divergence calculate equals a negative z and j hat minus x squared and k hat. That's what I have. Once I found a divergence, you remember the Stokes theorem left hand side is the divergence, the right hand side is the line integral. So this is the line integral itself. Now it's a little more convoluted because in Green theorem only have essentially two terms adds up, but for the Stokes theorem you could have three-dimensional ones, so that's why I leave it there. So this is the so-called right hand side of the Green Stokes theorem that you have. The equation that we have, which define is the surface integral. The surface integral as well as the line integral is in this particular plane, and so the line integral I can arbitrarily choose which one that I want. For instance, in this case, I can choose my plane is on the z equals 0, which is xy plane. So therefore, I drop out z. In the beginning, you see we have such complicated equations here because z now we choose the surface. We're allowed to choose any line as far as the surface stays the same. So we can choose this one here. That's what we have. Once we know that, so then we come back to the so-called standard equation, which is the Stokes theorem. Stokes theorem on the left-hand side, or right-hand side, whatever, it's the loop integral. It's a dot dr, and that's just like force time displacement. It's just the work. Now, in the beginning, when we talk about Green theorem, we only have two terms. But now, in general, you have three terms. You see here, term number 1, term number 2, term number 3. So the three terms will be available for you to work on. The good thing is about what we are choosing here. We're choosing the xy plane, so z equals 0. So this term automatically drops out. We could, crazy enough, we choose another surface, but the result stays the same. There's no difference. And now, here we have two terms which is involved. First we have ax and then ay. Let's look at ax. So here is our function that's a. So it only have the ax component, which is this part. It does not have ay component. You see, here is the x component, here is a z component. So therefore, my ay equals 0. So this makes integral is easier. So when we finish this integral, and we should be good. Now, to do this integral, it's not easy because x and y are not independent. So it's subject to this particular, the equation, which is over here. Commonly, when you have these equations like this, what you need to do, you need to convert them to the polar coordinate. So this is always a technique that whenever you have the expression like a circle like this, you always convert them to polar coordinates. You purposely choose x equals 2 cosine theta. The trick was that if you plug these guys into this equation, 2 squares go 4, so these 4 cancels out. First term essentially have cosine squared plus the second term will be sine squared because I have 3 here. So now when you want to do that, you just plug in the y here, x here. So then you just substitute all of these things into the same equation, which is like this. Now here's another technique you need to remember. You see we have a cosine theta squared, sine theta, sine theta. Now I'm going to combine these two sine together. The sine square and the cosine square together. So then it becomes 2 parentheses parentheses 2 sine theta cosine theta and squared, because this will give me cosine 2 theta, so this integral becomes much simpler. You can convert to double angles in this fashion. Originally have 2 theta and it becomes 4 theta, and that's integral. When you finish the integral, you get a negative 6 pi. So this essentially is finished with the line integral on the right hand side, and you could do the same thing the other part with the line integral. But now remember, the previous one we got a negative 6 pi, and here should be positive 6 pi, because you see the angle is not counterclockwise that I had before, and this should be counterclockwise. So therefore, if you add these two terms together, you get a 0 here. And that's the final results you are going to have for this particular problem. And so that is the final results.